Okay, so for our first example of an optimization problem, we're going to determine how to construct a box that has as much volume as possible. Now this is a very, very classic calculus problem. So suppose we are given some sort of sheet of cardboard. So let me undo that. So we're given a rectangular sheet of cardboard like that. And so I'm going to add some dimensions. Okay, so the idea is we're going to cut away the corners like this. Okay, I guess, let me see if I can. Okay, so I'm going to just copy and paste this thing. So I'm going to make an equal square cut out of all four corners of the box, like that. Okay. All right, so basically, I'm going to make a square cut out of each of these corners. Now, therefore, I can make folds in the box. I can fold it here and there. So this is started with a rectangular sheet of cardboard, making a fold there and there. So the idea is, let me add some dimensions. So suppose that this sheet of cardboard is 6 inches by 15 inches. Why not? So and you can see the pattern of how I'm cutting the cardboard. I'm cutting the square out of each of the corners. So now these corners are missing. Gone, 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 and gone. And these pieces become flat. So I'm going to fold this piece upward. I'm going to fold this piece upward, fold this piece upward, and then this piece gets folded. And then I end up with a nice, so that's this piece right here, and then along that way. So then the side of the box becomes that piece, and then like that. So we end up with a nice, cardboard box. Okay, so given this sheet of rectangular cardboard, 6 inches by 15 inches, what's the maximum volume of a box that we can make out of this? So how do we construct a box with as much volume as possible, given the constraint that we only have, this finite amount of cardboard? So before I proceed, let me just add one additional problem-solving suggestion or piece of advice. Don't define variables unnecessarily. So you can start by saying, oh, this is x, this is y, that's z, and then the volume's x, y, z. Then you need two constraint equations. Actually, you can get away with this particular problem with defining only one single variable. And let me show you how to do that. So really, the box has fixed dimensions, 6 by 15. And what you have control over is how large to make these squares. Well, that's only a single variable, because you can say I'm going to cut out a square of length x, right? So this is a square of side length x. So x becomes the variable. X, 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 x. So each square that I removed has a specific size, x by x. And x is our unknown. So the question really boils down to, how do I select x to make a box with as much volume as possible? If and feel free when I do these problems to pause the video and think about it. How would you go about doing that? Okay, so next, we need to figure out the volume. So we need to express the volume as a function of this variable that we have control over. So we have control over the variable x, and then we need to express the volume, output volume, as a function of x. Okay, so we need, for the volume, we're going to need this length, that length, and this height. Now the height is just the length of this fold right here, so the height is going to be x. And the other dimensions are going to be this one right here, so that corresponds to this front width right here, and then this dimension right here. So what is the length of this, what's remaining, what's the length of this one right here? Well, note that we start off with a 6-inch side, and we cut off a piece of length x right there and a piece of length x there. So we're removing a total length of 2x from this side. So this length is going to be 6 minus 2x, and this becomes 6 minus 2x. Similarly, this length right here, we started with 15 inches, and we're removing a piece, length x. So this is going to be 15 minus 2x. So this goes 15 minus 2x. So the total volume of our box that we can construct is x times 6 minus 2x times 15 minus 2x. So that's our volume as a function of our variable x, which is free to move around. So let's expand this, and so it's x times 6 times 15. I think that's 90. Pretty sure. So yeah, 90. So that would be, so we're going to FOIL. 6 times minus 2 is negative 12. So then we get negative 12x minus 30x. So 30 and 12 is 42. So we get minus 42x. And then finally, 2 times 2 is plus 4x squared. So our volume is going to be 4x cubed minus 42x squared plus 90x. So now it's very promising. Well, we can optimize this, right? This is just a polynomial. We can take the derivative, set it equal to 0. Now the other thing that we want to watch out for is the domain. So the domain for x is going to be on 0 to 3. And the reason is that we look at the shortest side of this rectangular sheet of cardboard, which is 6 inches. Well, if x is 0, that's basically, a degenerate solution. I've got a box with 0 height. It's 6 by 15 by 0. So the volume will be 0. If I go up to 3, I'm using exactly half of the shortest side, which means this length is going to be 0. So it's just going to fold up like that. And it's going to have 0 volume. So I can't go beyond 3 because I only have so much cardboard to work with. So the domain of this function is 0 to 3. And 0 and 3 are roots of this. So at both of these points, we're going to have a local minimum. In fact, global minimum at x is equal to 0 and x is equal to 3, because the volume has to be positive. Okay, so now let's look for the critical points that are inside the domain. So dv dx, 12x squared minus 84x plus 90. It's a quadratic, so then we set it equal to 0. That's how we find critical points. So we set that equal to 0. And that's a quadratic equation, so we know, well, first of all, is there any common to just simplify it? I think divided by 2. That's the same as, so if we divide this by 2, we get 6x squared minus 42x plus 45. 3 goes into everything, doesn't it? 42 over 3 is 14. So this is the same as 2x squared minus 14x plus 15 is equal to 0. So essentially I divided it by 2, then I divided by 3. So I divided this equation by 6. You don't have to do that, but it just makes, why not? Okay, so we know the roots, quadratic formula. So it's minus b, so that's plus 14, plus or minus the square root of b squared minus 4ac. 2 times 15 is 30. 4 times 30 is 120, and then over 2a. So 14 squared, 196, minus 120 is 76, square root of 76. So this is basically 14 plus or minus the square root of 76 over 4. Now, I can simplify this, and the square root of 76 is 8. Okay. So I can simplify this a little bit more because I can, there's a common factor of 2, so it's 7 plus or minus the square root of something over 2. Now, when I'm taking a factor of 2 and pulling it into the square root, I have to square it. So 76 over 4 is 19. So it's 7 plus or minus the square root of 19 over 2. So those are the two critical points. So 7 plus square root of 19 over 2 is 5.679 dot dot dot. 5.679 is not inside our domain. See how important the domain is. So let's look at the other one. 7 minus the square root of 19 equals 2.6411 divided by 2, 1.32. So that is inside the domain. Okay. Now, we have a domain 0 to 3. The volume of the box is equal to 0 at both of those points. In between, this volume has to be positive. And we only have one critical point at 1.32055, so that's going to have to be the maximum. But suppose we want to confirm that this is the maximum, we can use the second derivative test. So sometimes the second derivative test is not easy to use because we have really complicated derivatives. This is a polynomial. It's really simple to check the second derivative. So d squared v over dx squared is 24x minus 84, and that's it. Derivative of 90 is 0. So remember, this was the v dx right there. So let's take a second derivative. We get 24x minus 84. Okay, x, the critical point's approximately 1. It's 1.3. 24 or even 30 or whatever 24 times 1.3 is, it's not as large in size as 84. So 24 minus 84 is negative. So v double prime of 1.32055 is less than 0. Negative second derivative means you're concave down. Concave down, it's a maximum. That confirms that this is the maximum volume for the box. So we should make a cut. X should be 1.32055. And if that's x, the box will have dimensions 1.32055 by 6 minus 2 times x, 3.358899, and then 15 minus 2 times x by 12.358899. So the total volume of the box is 54.819079993 inches cubed. So a little shy of 55 cubic inches. That's so if it says if the problem says what's the maximum volume of this box? Okay, you're going through all this to optimize on x, and you think the answer might be x. So this is another. Let me go back to read the problem. So okay, you read the problem. You have a sheet of cardboard, 15 inches by 6 inches. Find, and you make square cuts on the corners, and you fold up the flaps. Find the maximum volume of a box you can make with this sheet of cardboard. Okay, well, we did all this work, right? It took some time. We set up this stuff. We defined our variable x. We went through. We did the second derivative test. And you say, hey, okay, x is 1.32055. You might suspect, oh, there's the answer, 1.32055. No, the problem asked for what's the maximum volume of the box. It's not over until you find the maximum volume of the box. So you actually have to plug this back in and say, okay, the maximum volume is 54.819 cubic inches. Another thing to be careful about is a problem that doesn't tell you what the variable is. So here's just a sheet of cardboard, rectangular sheet of cardboard, find the maximum volume. Suppose you say x is equal to 1.32055 as your answer. Okay, well, what's x? Nobody knows other than you. You defined the variable x. You defined that variable to solve the problem. But unless it's actually stated in the problem statement, nobody's going to know what the variable x represents. Now, sometimes it will be obvious. Okay, we see what you did. You set up x up like this and that, and there's your answer. But other times, not necessarily. I've graded problems where I had some random, w is equal to 90. What's w? Grading a problem, you have no idea what the variable. Your graders and your teachers are not mind readers. So that's why, again, always clearly write down, let x represent, the side length of the squares you're cutting out of the cardboard box. Then draw a picture. There's x. That's what x is right there. That way, this is just general advice for writing up homework solutions or exams. That way, when somebody goes to grade it, they're going to say, oh, I know what you're talking about, and they're on the same page as you. And also, as I mentioned in the last video, it prevents confusion, your own confusion. You can start off thinking, oh, these are the variables, and then you work a little bit. It's a long problem, and then suddenly you're using x to mean something else, and you might have done all the steps correctly, except you suddenly use x to represent something else because you didn't clearly write down and identify this is what x means, this is what y means. So make sure to always get into the habit of doing that.